So today in this lecture we are going to see about a signal flow graphs. So what is a signal flow graph? A signal flow graph, it is used to represent a control system graphically. So in a graphical manner. So already we have discussed about the block diagram reduction, block diagram representation. So in block diagram representation also it is used to represent any control system diagrammatically, right, or in a diagrammatical form. So here the signal flow graph is also used to represent a control system graphically. So this signal flow diagram, it represents actually it represents a set of simultaneous linear algebraic equations, right? So we can represent the linear algebraic equations in the form of signal flow graph. So the signal flow graph and the block diagram representation both gives same information, right? To find the transfer function, we can reduce the signal flow graph in the similar manner that of the block diagram reduction. So both these graphs or both these diagrams, these give same information. So let us see the terms that are used in the signal flow graph representation. So the first one is the node. So what is a node? A node is a point. It is just a point representing a variable or a signal. Node is a point, it representing a variable or a signal. What is a branch? Branch is nothing but a line segment joining two nodes, right? For example, so here there is a node, here there is another one node. If there is a line that joins these two nodes, and this is nothing but a branch. Okay, next transmittance. Transmittance is nothing but the gain. It represents the gain occurred by this signal when it travels from one node to another node, right? So when a signal travels from one node to another node, what is the gain obtained by that particular signal? That is called transmittance. Next one is the input node. What do you mean by input node? So input node, it is also called a source node. So this source node, it has only outgoing branches. So like this, right? So in this way, if a node is represent, it is known as input node. It will be having only outgoing branches. What is an output node? So output node will be having incoming branches, right? For example, so if this is an output node, this output node will be having incoming signals only. There is no outgoing signal from this node. Next one is the mixed node. So mixed node is having both incoming signal as well as the outgoing signal, or we can say it has both incoming as well as outgoing branches. Okay, the next is the path. What is a path? Path is nothing but traversal of connected branches, right? For example, here you are having a node. A signal travels from this path, this in this way, it reaches another node, right? And you are having some other node. So this is the direction of the travel of the signal. So this represents a path. Understood? What is an open path? Open path means a path, it starts from one node, starts at one node and it ends at some other node. This is an open path, right? So it starts at one node and ends at another node. What is a closed path? Closed path means it starts and ends at the same node. For example, if a signal starts from this node and it traverses in this direction and it reaches another node, and suppose if it reaches again back to the original node, then this is called a closed path, right? So it starts and ends at the same node. What is a forward path? Forward path means path from input node to output node, right? For example, if a signal travels from starts from this point and it travels in this direction, reaches another node, so this path is called forward path. So this forward path, it does not cross any node more than once. So it will cross any node only one time. So that is called a forward path. So it is a path from an input node to an output node that does not cross any node more than once. What do you mean by forward path gain? Forward path gain. So forward path gain means it is a product of the branch transmittances or the branch gains. It is nothing but the product of the branch transmittances or branch gains. This is called a forward path gain. What do you mean by an individual loop? So if a loop that does not cross any node more than once, so you are having a loop, and for example, here there is a node, a signal travels in this way, it reaches another node, and once again it reaches to its original position, original node. So this is a loop, right? This signal may travels in this direction also, but this loop is called an individual loop because here it does not touches any node more than once, so that it is called an individual loop. Next, what is a loop gain? So once the gain, or we can say the gain product of the gain of a loop is called loop gain, right? Next one is the non-touching loops. So there may be loops like this, right? There may be loop like this. If this loop is not touching with any other loop, and this one is called a non-touching loop. Here there may be another loop, right, like this. So here this one is also a non-touching loop because these two loops are not touching each other. This is called a non-touching loop. See here, uh, this loop touches this point, and this one is also touching at this point. So in between there is a signal flow. For example, here another one node is there, then these two loops are called non-touching loops because the loop that should not cross any node more than once. These are the terms that are used in the signal flow graph reduction or signal flow graph representation. The next one is the signal flow graph reduction rules. Let us see the signal flow graph reduction rules. The first rule is the incoming signal to a node through a branch is given by the product of a signal at a previous node and the gain of the branch. This is the first rule. So the incoming signal to a node through a branch is the product of the signal at the previous node and the gain of the branch. This is what the first rule. For example, let us see, here there is a node, it is represented as x1, and a signal travels from this node. This signal is represented as A, and it reaches another node x2, right? So the signal, the product of the signal gain can be, we can write the signal gain as x2 is equal to the output node, x2 is equal to A into x1. This is what the rule, right? For example, you just see another one node here, it is represented as x1, a signal A is traveling, A1 is traveling through this path and it reaches a node x3. We are having another one signal x2, another one node x2, and the signal through this node is A2 and it reaches the same node x3. Now the output signal x3 can be written as x3 equal to A1 into x1 plus A2 into x2. Okay, the output node or the incoming signal to the particular node through a branch is incoming signal to this particular node through a branch is nothing but the product of the signal at the previous node, right? That is the product of the signal means A into x1 and the gain. Okay, so this is what the first rule. The next rule is cascaded branches can be combined to a single branch. Cascaded branches can be combined to a single branch. or cascaded branches can be combined to give a single branch whose transmittance or the gain is equal to the product of the individual branch transmittances, right? For example, here you are having a node x1, a signal through the from this node is a, and it reaches another node x2, and once again the gain through this path is represented as b, and it reaches another node x3. Then this can be simplified as x with a signal with two nodes, right? X1, the starting node, the ending node is x3, right? Now the gain here at this point is the product of these two gains, that is a into b. So similar to the block diagram reduction, if you cascade two gain blocks, right, if you cascade two gain blocks g1 and g2, the resultant will be a single block with the product of the gain g1 and g2, right? Similarly here also, if two branches are cascaded to a single branch, then the gain is nothing but the product of the individual gains, The next rule is the parallel branches may be represented by a single branch with gain is equal to the sum of the individual branch transmittances, or the sum of the individual branch gain, similar to the block diagram reduction. So in block diagram reduction, suppose if you are having a gain block g1 and another gain block g2, if you add these two things, you will get the answer as g1 plus g2 in block diagram reduction, right? This can be replaced with a single block g1 plus g2. Understood? So here also you see, here there is a node, another node, output node, one signal with a gain of a is traveling from this direction, another signal with a gain b is traveling in the same direction, so that it is not a loop. Understood? It is not a loop because these two signals are traveling in the same direction, right? This signal starts at this point, ends at this point. Here this signal starts at this point, ends at this point. So this is not a loop. Now this can be replaced with a single branch with the gain is equal to a plus b. Understood? Suppose if this node is represented as x1 and this is x2, and now this one is x1 and this one is your x2, right? This is the rule number 3. The next rule is the eliminating mixed node. How to eliminate a mixed node? Mixed node means this mixed node can be eliminated by multiplying the transmittance of outgoing branch from the mixed node to the transmittance of all incoming branches to the mixed node. For example, you just see an example. Here there is a node, it is represented as x1, right? The signal, the gain through this branch is represented as a, and reaches another node, it is represented as x3. See another one node x2, right? And the signal through this branch is b, or the gain of this branch is b, and you are having another one node x4 with a gain of c. Now this is called a mixed node. This can be, so this extra branch, this branch can be eliminated by multiplying this gain with both of these branches. That is, this can be done as x1, node x1, another node x2. Now you need to multiply this c with this gain a, therefore it will be equal to a into c. And here also you need to multiply the gain with the c, so it will be equal to b into c, right? Now this node is your nothing but x4. Understood? This is your x4, so that we can eliminate this unnecessary branch. The another one rule is the rule number 5, eliminating individual loop. So in the block diagram reduction, we have seen, suppose there is an input r, right? If there is a summing point at this place, and the gain, forward gain is g, and the output is c, right? If there is a feedback path with the feedback path gain h, and if it is a negative feedback, the entire block can be replaced with a single block, isn't it? So we have seen this with the gain of forward gain divided by 1 minus forward gain into feedback gain 1 minus GH. In the similar manner in signal flow graph also, suppose just consider a node x1 at this point, and the gain through this branch is A, and it reaches another one node x2, and another one node x3 is there. The gain through this branch is B, right? And here, if suppose you are having a feedback like this, right? A feedback like this. See here, if this is a negative sign, then this one is a positive sign. Suppose if it is a plus, this one will be a negative sign. Understood? So here also, just consider these two, both are equal to plus, right? Therefore we can replace this loop with a single branch, that is the resultant will be x1, right? Here this is x2 and the final node is x3, right? Now this branch is A, this branch gain is A. Now we can replace this entire feedback loop, right? Entire feedback loop with a single line. What will be the gain? Similar to this one, the gain will be equal to B divided by 1 minus B into C. The forward path gain is B, right? So B divided by 1 minus B into C, because here minus sign comes because it is a positive feedback. Understood? So these are the 5 signal flow graph reduction rules you need to remember in order to solve the signal flow graph problems, right? The next one is the Mason's gain formula. Actually, this signal flow graph is introduced by the scientist called Mason, right? He introduced a formula called Mason's gain formula. Mason's gain formula, right? So what is this Mason's gain formula? The transfer function of the system or transfer function from a signal flow graph can be obtained by using the formula T of S. T of S is equal to C of S, output, the Laplace transform of the output divided by the Laplace transform of the input, R of S. C of S divided by R of S, right? The Mason's gain formula states the overall gain of the system. Overall gain of the system as overall gain of the system is equal to, that is T equal to T, or T of S is equal to 1 by delta into summation K Pk into delta K. Pk into delta K. This is what the Mason's gain formula, right? So let us see what are all these things one by one, right? This T represents T of S, or the transfer function of the system. This is nothing but the transfer function T of S. Okay, T represents the transfer function of the system, entire system. Okay, next Pk represents, here this Pk represents, this Pk is nothing but the forward path gain of forward path gain of kth forward path. Okay, that is nothing but the gain of the any forward path. Suppose if there are 5 forward path, then you need to write the forward path gain P1, P2, P3, etc., right? P1, P2, P3, etc. So this represents the forward path gain. It is nothing but the gain of any particular forward path. This is what Pk. Next one is the K. K represents, what is this K? It represents the number of forward path in the signal flow graph. Number of forward path. Okay, number of forward paths in the signal flow graph. How many forward paths are there? That is nothing but K. Understood. Next one is the delta. So you are having a formula to find this delta. It is nothing but 1 minus sum of individual loops. 1 minus sum of individual loops plus sum of gain products of all possible combinations of two non-touching loops. Sum of gain product of all possible combinations of all possible combinations of two non-touching loops, right? Next, minus sum of gain product of all possible combinations of three non-touching loops, okay. Next, plus sum of gain product of all possible combinations of four non-touching loops, okay, four non-touching loops, minus etc. In this way it goes. So the delta means 1 minus sum of individual loops, 1 minus sum of individual loop gains, okay, individual loop gains, right, plus sum of gain product of all possible combinations of two non-touching loops, right, minus this will come, first one is minus, next one is plus, next one is minus. So in this way alternate sign will come. Understood? So please remember this formula, delta equal to 1 minus sum of individual loop gains plus sum of gain product of all possible combinations of two non-touching loops minus sum of gain product of all possible combinations of three non-touching loops plus etc. This is what the Mason's gain formula, right? So now let us see with a simple example how to reduce a block diagram, or how to find the transfer function from the signal flow graph. Understood? We just see a simple example. This is what the problem, right? Here you see there is a node R of S, right? Here the gain is 1, it is unity gain. You are having another node, this is node number 1, this is node number 2, and this one represents the gain, okay, this one represents the gain. You are having another node, right, node 3, and the gain at this point is G1, right. You are having another node, it is node 4, and the gain is represented as G2, right. You are having another node 5, right, and the gain at this point is G3, right. You are having another node 6 with a gain of G4, right. You are having another node 7, here the gain is G5, right. You are having another node, final node 8, here the gain is equal to 1. Understood? Here some feedback loops are there, right. Let us see the feedback loops. Here this one is a feedback loop with a gain of minus h3, and you are having from node number 5 to node number 2, node number 5 to node number 2, you are having a forward path with a gain of G6, okay, and you are having another one feedback path from this node 5 to node 3, this is known as minus h2, right. You are having another one feedback path from node number 4 to node number 3, right. This is minus h1. This is what the problem given. You need to solve this problem by reducing the signal flow graph, or you need to find the transfer function, the final transfer function of the system, right. How to find the transfer function? So let us start writing the forward path gains first, right. So first of all you need to write the forward path gains. So what are the forward paths? Here how many forward paths are there? Forward path means a signal starts from one node, ends at some other node, right, that is known as forward path. So here you see you start from this node number 1, so you can traverse in this direction 1 to 2, Next the signal travels from 2 to 3, right? Just I am drawing this diagram again. So here this node number 1, node number 2, then it travels from 2 to 3, then 3 to 4, then 4 to 5, then 5 to 6, then 6 to 7, then 7 to 8. Understood? So this is a complete forward path. So signal starts at node number 1 and ends at node number 8. So this is known as a forward path. So I am redrawing this forward path again, starting from node number 1. So totally there are 8 nodes: 2, 3, 4, 5, 6, 7 and 8, right? So here the first gain is 1, the second gain is G1, right? The second gain is G1, the third gain is G2, right? The next one is G3, the next one is 5 to 6, you are having G4, right? 5 to 6 you are having G4, next 6 to 7 you are having G5, right? Finally 7 to 8 you are having 1. This is a complete forward path. Therefore the forward path gain, how to write the forward path gain? P1, right? Forward path gain P1 of this forward path, which is nothing but the product of the individual gains. So 1 into G1 into G2 into G3 into G4 into G5 into 1. Understood? Therefore P1 equal to G1, G2, G3, G4 and G5, right? This is what your first forward path gain. Understood? What is the next forward path? You see, the signal starts from node number 1. Understood? It reaches 2, so it can take this path also. Understood? Because this is also a forward path. Understood? So the signal travels in this direction. Okay, this is also a forward path. Understood? And it reaches 5, so it cannot come this way, because see the direction of the signal at this point, this forward direction. So after reaching this node number 5, it will travel in this direction, right? Node number 6, next node number 7, finally it reaches node number 8. So this is another forward path. Understood? See here, so I am drawing this forward path again. Node number 1, next node number 2, next node number 3, 4. It is not touching with node number 3 and 4. It travels 2 to 5, node number 2 to 5. Therefore node number 3 is simply there, node number 4 is also there, node number 5, right? So from 2 to it reaches node number 5. So the gain at this branch is G6. Okay, this is G6. Next 5 to 6, 5 to 6, 6 to 7, 7 to 8. It reaches the output node. So here the gain is 1, 6 to 7 it is G5 and 5 to 6 it is G4. This is another forward path. Understood? So we can write the forward path gain P2 is equal to, the forward path gain P2 is equal to, here this gain is 1, right? So 1 into G6 into G4 into G5. Understood? Or we can write this as, which is equal to G4, G5, G6. Understood? This is what the forward path gain 2. Is there any other forward path? Is there any other forward path in this diagram? There is no forward path, because the signal travels, this is one forward path. The signal can travel from node number 1 to directly it can reach to node number 8 in this way. The another way this signal can travel is in this direction, right? In this direction also it can reach the output node. So suppose if the signal is coming at node number 3, it cannot go to node number 4 through this way, because this is a reverse path. Understood? And also it cannot travel in this direction also, because this is also a reverse path, right? So this is not a forward path. So from this point also it cannot, if the signal comes through this point, it will touch this node 2 times. Forward path means a path which does not, a branch does not touch a node more than once. புரியுதுங்களா? So more than once, it should not touch a node more than once. Therefore this diagram has only 2 forward path. Therefore we have written the forward path gains P1 and P2, P1 and P2, and therefore the value of K is equal to 2 here. the value of k equal to 2. 2 represents the number of forward path. Next one is you need to find the individual loop gains. Okay, you need to find the individual loop gains. How to find the individual loop gains? Individual loop gains. See how to find the individual loops. So what are all the individual loops present in this diagram, right? Here you see the signal starts, this one is, you seems to be a loop. See here, it seems to be a loop, but here the signal starts from this point, point number 2, node number 2, reaches 3, reaches 4, reaches 5, but it cannot travel this way, it cannot travel in this direction, right? In this direction it cannot travel, therefore this is not a loop. See here at node number 3, starting from node number 3, it can reach node number 4, once again it can reach node number 3, starts from a node and reaches to the same node, that is called a loop. Understood? So this one is a loop. Understood? Starts from node 3, reaches 4, and once again it comes back to the original node. This is a loop now. Understood? This is called an individual loop, right? See here, this is one individual loop we have identified. This is not a loop, right? See here another one loop. This signal can start from point node number 3 and it can reach node number 5, right? And it can take this path to